So thank you very much for the introduction. Let me just say straight away that if you'd like to get a copy of the slides, there's a link shown here, which I've also put into the chat. You're welcome to download that, and there's plenty of links within the slides to the things I'm talking about. So I'd like to talk about communicating applied mathematics, specifically communicating research, and doing so using the various tools that we have available today. And I think a good place to start is just by looking at what I might call the research cycle. So this is the way things typically go. You have a research idea. You may or may not want to try and get some funding to support following up that idea. You do some research, you eventually write a paper, and you then hopefully are able to publish the paper. And at some point you may give a conference talk on the work. And this is the typical cycle. And the sort of having published the paper, this is the climax of the whole process. And this whole process is going to take many years, of course, certainly many months. Publishing the paper, then you typically will go on to the next research problem. And so what I'd like to suggest is that there may well be an argument for, depending on the type of the research, trying to promote it to a wider audience than just the usual experts in your particular area. So people in other areas who might be able to make use of the ideas in the work. I put down the word feedback there to remind me to make the point that, at least in my experience, when you publish a paper, after all this work, typically the paper appears and then there's silence. You rarely get any quick feedback on what you've done. It could be many months, certainly quite a long while before the paper is even cited, and you tend not to get much feedback. And what I'm going to talk about, the things I'm going to talk about today, are at least, if nothing else, ways of getting some good feedback pretty quickly on what you've done, which can be extremely useful. So rather than talking generalities, I'd like to give you 3 examples to illustrate the point I'm making here. And so the first example is about numerical differentiation. And so the idea is we have a function f, we only know how to evaluate f, and we would like to approximate the derivative. Now there's a whole theory of finite differences in numerical analysis, and just about the simplest finite difference approximation is shown here. So you simply basically take the definition of limit and just plug in a small but finite h. And so for small enough h, this should be a good approximation. And in fact, if you expand in the Taylor series, look at the error, you find, of course, it's of order h. So as h gets smaller, the error should go down linearly. But if you try this on the computer, and I've done so here with the exponential function at x equals 1, and this is in double precision in MATLAB, you find that the error initially indeed does go down linearly, but then around about here it starts to oscillate wildly and then start to increase as h gets smaller and smaller. So this is a well-known phenomenon, and the problem is that at this point here, rounding errors are starting to become of similar size to the truncation error, and eventually the rounding errors dominate. You're dividing by a smaller and smaller number that magnifies the rounding errors in the numerator there. And it's easy to do a bit of analysis to work out the optimal value of h, which is trying to estimate where the minimum point here, and that formula gives you this dot. So it's well known that this is a problem, so you're only going to get about half the precision in the derivative if you use this approach. But there is another method that's not very well known, and it's got some resemblance to the finite difference. So now I'm assuming that f is the analytic function, and x is real and f of x is real. So what we're going to do here is not just add h, but add the imaginary unit times h. So we now have f of a complex number. That will be complex in general. We're going to divide by h again, but then take the imaginary part. So this is our approximation. And again, if you expanded the Taylor series and equate imaginary parts, you find the errors big O h squared, because the first term you've missed out will be order h cubed. And interestingly, and very importantly, this evaluation is not affected by rounding errors. Now, many years ago, I was visiting the National Physical Laboratory. I remember Maurice Cox telling me that at NPL, they used this approximation with h equals 10 to the minus 100, which is a much smaller value than I thought of taking. But in fact, it doesn't matter how small you take h, as long as you don't get underflow, this will still work numerically. What's essentially going on is we're doing a kind of automatic differentiation with the IH term functioning like a symbolic variable. And this will work as long as the evaluation of f itself doesn't employ complex arithmetic. So let me give an example. So here we've got f is arctan of x over 1 plus e to the minus x squared. I'm taking x equal to 2. Here's the exact derivative to the 15 decimal places shown. The complex step method with h is 10 to the minus 100 gives all correct figures. The forward difference with h, the optimal value, gives us only about one figure correct. The forward difference with a tiny h, avoiding a round off, gives us one digit correct. The forward difference with the optimal value gives us only about half the digits correct. So this complex step approximation is really doing its job here. It's giving us full accuracy for almost any small h, really any tiny h will do here. So this is an example of what Higham called, well, this little maxim of his, that the shortest and best way between two truths of the real domain often passes through the imaginary axis. And of course, I'm sure people know many other examples of this. For example, approximating real integrals by using a contour integration instead. So this is an example of that kind of thinking. So what's the history of the idea? Well, it first appeared in a 1998 paper by Squire and Trapp in Higham Review. It's just a short 3-page paper, and you can see it's been well cited. The idea sort of goes back to a paper by Linus and Moeller. They don't explicitly give the formula, but they have similar thinking in that paper. Tim Kelly mentioned this in his book on Newton's method. There's been a few papers in the aerospace engineering literature that have used this method, one by Mike Giles here, for example. With my former PhD student, Alwad Al-Mohi, we extended this to matrix functions so that we're now approximating the Frechet derivative of the matrix function. Rob Corliss and Nick Fillion included this in a recent book of theirs on numerical methods. Cleve Moeller's mentioned it in the blog post. There's a recent book on deep learning that has mentioned this, which has probably given it quite a bit of publicity. And again, a recent Symbolic book. But there's not a lot of mentions in the literature, but certainly some. So when I was Symbolic president, I had a monthly column in Symbolic News, and I decided to write about this method. I thought it would make a nice short column. So that was published in 2018, and I got quite a bit of feedback. People basically saying, I wasn't aware of this idea. It works really well. I'm now using it in my undergraduate teaching. I also published a blog post on the method last year. Again, got some good feedback. Someone saying it's totally changed my thinking about numerical differentiation. So people really like this method. And there was also some couple of tweets there that were responding to the recent blog post. And one person actually used this in a rather interesting way. So the Shader Toy, I think, it's a website for visualizing and rotating in 3 dimensions various structures and shapes. Not mathematics specifically, it's used for gaming and things like that. But somebody wrote a little code that uses the complex step approximation to visualize this object here. And if you go to this link at the bottom, you'll find that this rotates within your browser. So that's using complex step to get the derivative. So what I conclude from that is that people are very happy to hear about this method, but they wouldn't have heard about it otherwise because they don't, they wouldn't have looked in the right place in the research literature. So it's well worth doing even more, I think, to promote this method because of its wide potential use. So that's example 1. For example 2, I want to go back to the 1960s. And so we were at the early stages of scientific computing. We'd had the first digital computers in the 1940s. One of the first high-level programming languages was Fortran. Fortran was developed in the US by IBM. And in Europe, there was a language called Algo 60 that had been developed. And this was really developed with structured programming principles in mind. And for a while in the 1960s, Algo 60 was the main language in which people published computer programs. And the journal Communications of the ACM used to publish programs in the early 60s. So this is a complete paper, just this very short program to compute log of a complex number. So that in the 1960s could be a paper. Now, why do you need a paper on this? Well, Algo 60 did not have a complex data type. So you had to represent a complex number as the real and imaginary part. And then you had to essentially program the complex arithmetic. So that's the reason for this code here. So that was published in 1961. And I should say what I mean here by log. So log is the principal logarithm that has imaginary part between minus pi and pi. Okay, so that's the branch that we're talking about. And a little later, you'll see the z to the alpha. So z to the alpha is defined as e to the alpha log z. So it's the principal branch of the alpha power. So after that paper had appeared, a year later, Relf published certification of algorithm 48, but he found some problems. So that program on the previous slide fails for real part 0, and the imaginary part is on the wrong range for the principal logarithm. And even worse, there's a call to the function log here. Well, log is actually log to the base 10 in Algo 68, in Algo 60, and that should have been a call to ln, the log to the natural base. Now, what that tells me is that this program had probably never been run, because it would give the wrong answer for almost any input. And this is 1961. I suspect that there weren't actually any working Algo 60 compilers at the time. So I think this author had written the code and not had the chance to run it. So that's understandable that there'd be some problems. Then there was another paper pointing out some more problems to do with the division by 0 was possible. So the signs were incorrect in a different way than Relf had identified. Collins now publishes Remark on Remarks, and Collins notices that Johnson and Sangren in their correction end up with log 0 being defined as 0 and have got some minor signs missing. So finally, Collins did a new version of the algorithm in 1964, which is correct. So it took experts at the time 4 years to get a correctly working code for log of a complex number. So that's an indication that dealing with multi-valued complex functions is tricky. There's many pitfalls. So following up on that idea, here's the cover of Ian Stewart's book from a few years ago, where he identifies 17 very important equations. Well, one of them is this log equation here. The log of a product is the sum of the logs. And of course, in this context, x and y are positive real numbers. But what if x and y are complex variables? Is this equation still true? And this is a question that's come up in my work. So one thing you might do is you go to your bookshelf and find a book on complex analysis and see if you can find this equation. So here's a Springer book from 2011. And yes, 9.1, equation 9.1 says that the log of a product is the sum of the logs. So it would appear that this formula is actually true. And there's a little proof there even. But if you turn the page, you find that the statement that equation 9.1 is true as long as you take the appropriate branch for each occurrence of the logarithm. So this is not true with log the principal logarithm. You might have a different branch in each occurrence of log. So that's quite different than the equation I was asking about with a particular log. And in fact, this kind of situation is not unusual. If you look in the NIST Handbook of Mathematical Functions, this wonderful book edited by Frank Olver, that's a successor to Abramovitz and Stegun. If you look at, for example, the addition formulae for arc sine and arc cos, again, it's stated that these formulae hold with appropriate choices of the branch for each occurrence of the relevant function. So in practical computation, I'm interested in working with a particular branch. So I want to know, will this formula be true if I plug in Fortran's arc sine, for example? Another indication of how things can go wrong, an older version of MATLAB, you could ask for an arc cosh of -4, and you get one answer from MATLAB itself and a different answer from the Symbolic Toolbox, where the real part has a different sign. And so there was a bug in the Symbolic Toolbox here that was fixed very quickly once it had been spotted. And there are other identities involving complex numbers that can also have some surprises. So we wouldn't bat an eyelid at the identity I've written down there. But if you write it down in a different form, z minus 1, z squared minus 1 now, it turns out this is not always true now. This is only true for z in a certain, arg z in a certain interval. So we need to be careful when dealing with multi-valued complex functions. And what tools do we have for doing so? Well, there's a very nice tool that's not very well known called the unwinding number. Not to be confused with the old notion of winding number. The unwinding number is defined in this way here for any complex z. So you take z minus log, the principal log of e to the z, and you divide by 2 pi I. And if you rewrite this expression, you'll see that basically the unwinding number is giving us a correction term for the equation z is log e to the z. It's not hard to show that this is an integer. uz is an integer, and it's 0 if and only if z lies in the complex plane in the vertical strip between minus pi and pi. So this function was defined by Rob Corliss, Hare, and Jeffrey in 1996. Apostle's 1974 book on complex analysis gives actually a special case of this. So is this useful? Well, yes, it is. And so here was my question about the log of a product. So it turns out the log of a product is equal to the sum of the logs, except for a correction term that can be written in terms of the unwinding number. And the proof is incredibly simple. So you just write z1 as e to the log z1, same for z2, you add exponents here, and now you just apply the definition of an unwinding number. So that is the correction term for this identity. And you can do the same thing for the power of a product. So z1, z2 to the alpha, is that equal to z1 to the alpha, z2 to the alpha? Well, not in general. There is a correction term, again involving the unwinding number, and with a nice simple proof once again. And these results generalize to matrices, which is an even more complicated situation. But there, the unwinding number and its generalization, again, gives you the perfect correction term for these identities. Going back to my square root identity, if I use the result on the previous slide, if I take this as my z1 and this is my z2, I get the correction term from the previous theorem. And if I then do a bit of analysis on this term, I can indeed show that that term in yellow is equal to 1. But with things the other way around, with the z minus 1 and z plus 1 doing the same trick, I can see using the unwinding number that it will not always be equal to 1. The correction term will sometimes be non-zero. So it's a very useful tool for dealing with this sort of analysis. Now, a little bit of history then on this method. So Corliss and colleagues defined it in 1996. That paper's not been terribly well cited, especially by comparison with another paper that Corliss wrote on the Lambert W function with Knuth. The Lambert W function is a log-like function that has a number of applications, including in delay differential equations. So you see, this has been cited 100 times more. It certainly helps to have Donald Knuth as a co-author. But the unwinding number, it seems to be relatively little known. I've mentioned it in my Higham book on matrix functions. I noticed that Stack Exchange, somebody mentioned it in answer to one of the problems there. Rob Corliss and Fillion mentioned it in a recent book of theirs. I've developed an extension to matrices with my former PhD student, Mary Abrahamian. And I've written a couple of blog posts on this method, on the matrix version of the function. I also devoted one of my Science News articles to it. So the unwinding number is, I think, incredibly useful, but still seems to be, to my mind, relatively little known. So this is an example of something where I think we need to do much more work to promote the method, because I think people who want to work with multivalued complex functions will find this extremely useful. So my last example is rather different, and this is something that goes back to an email I had at the start of the year. So I had an email from an EFX Algo Trader. Well, what does EFX stand for? That stands for Electronic Foreign Exchange. And the gist of this email is that this person has some covariance matrices, and they're a bit uncertain about some of the elements in the matrix. Now, a covariance matrix is positive definite. And they were asking, if I set some of these elements to 0, will the matrix retain its positive definiteness? So in particular, if we think about a correlation matrix with elements between -1 and 1, if I set all the elements less than 0.5 to 0, will I still have a positive matrix? That was essentially the question being asked. So my reply to the email was that, well, that's an interesting question. I don't know the answer. I'll have to think about it and I'll get back to you. And I had a look around and I couldn't find an answer to this anywhere in the literature. It may well be there, but I couldn't quickly spot it. So I'll explain to you now what I did. I decided to look at a slightly more general problem. So rather than set the ij element of the matrix to 0, let me just add t to the ij and ji entries. So I'm adding t times this matrix eij here. So the question now is, I'm going to ask is, when is AT positive definite? For what values of t is this perturbed matrix still positive definite? Now, eij is a symmetric matrix with just two non-zeros. It's got a 1 in the ij and the ji positions. And it's easy to see it's got eigenvalues -1 and 1, and then n-2, 0 eigenvalues. And we can rewrite it in this form here, pp transpose minus qq transpose. So p will be the eigenvector corresponding to eigenvalue 1, and q an eigenvector corresponding to -1, and these vectors are orthogonal. So we're adding a multiple of this matrix to A, and what does that do to the eigenvalues of A? Do they all stay positive? Well, certainly adding pp transpose will increase the eigenvalues in general, and then taking off qq transpose will decrease them again. But that doesn't tell me a great deal. It doesn't really answer my question. So I need to know a bit more about the effects of a rank 1 perturbation. Well, there's a great theorem called Weyl's theorem that is very useful here. So we have a symmetric matrix, eigenvalues lambda1, lambda n the smallest up to lambda1 the biggest. And let me just describe this for n equals 4. So let's suppose our 4 eigenvalues are lambda4, lambda3, lambda2, and lambda1. And let's add pp transpose, a rank 1 positive semi-definite perturbation. Then Weyl's theorem says that the new eigenvalues, there'll be 1 between lambda4 and lambda3, there'll be 1 between lambda3 and lambda2, 1 between lambda2 and lambda1, and 1 bigger than lambda1. So the new eigenvalues interlace the old eigenvalues. They lie between the old eigenvalues. So we have interlacing for this special rank 1 perturbation. We then have to take off q transpose, and we can apply the same argument again. So if we start with the mu's, after the taking off a rank 1 perturbation, there'll be 1 eigenvalue to the left of mu4, there'll be 1 between mu4 and mu3, and so on. So again, we get the interlacing. But the point is there'll be only 1 eigenvalue to the left of mu4, and so only 1 potential negative eigenvalue. And I've just written down there the same inequalities in the general case. But the conclusion is there's at most 1 negative eigenvalue. And the reason that's nice to know is that if we want to check for definiteness, we now only need to check the determinant. Because in general, a matrix could have positive determinant and not be positive definite, because it could have an even number of negative eigenvalues. But here, we've only got at most 1 negative eigenvalue. So I only have to check whether the determinant is positive. And that's not too hard to do using a few identities. So we can show that the det is positive as long as t lies on this interval here. Now, B is the inverse of A. B is also a post-F matrix if A is post-F. And the denominators here is certainly positive because for a post-F matrix, you have this inequality for all I and j. So I can conclude as long as minus aij lies in this interval, I will retain definiteness. So let me show an example. So here's a 4x4 matrix called the Lehmer matrix. I think this has some number theory connections. And if I apply that criterion, I can check that every off-diagonal element can be set to 0 and not destroying definiteness except for 1. And the exception is this half here in the 2-4 position. If you set that to 0, you lose definiteness, and this picture illustrates that. The blue is the determinant of AT. The red is the smallest eigenvalue as t varies. And so we want to be between these black dots, but if we set A24 to 0, we're essentially at this vertical black line here. We're just outside the interval. So you can't go any lower than 0.0047 and retain definiteness. So having done that, I thought, well, I might as well write a blog post on this. There's certainly not anything worth publishing here yet. This may be not new. I don't want to try and make this into a paper. So I published a blog post, and I sent the link to my correspondent and said, here's what I know, and I think he was quite happy with what I provided. And I've also identified what I think are a couple of open problems in this blog post about how you can set more than one. Can you set more than one element at a time to 0 rather than doing it just one at a time as I've done here? So that's another way of promoting or disseminating work is via a blog post, and I'll say more about that in a moment. So I think from these examples, we can see that a journal paper itself might not widely disseminate an idea. You tend to publish in a specialist journal, it's read by your peers. People in other areas may not ever see that work. Now, and also we've seen, particularly with the complex step method, that people are really happy to hear about new techniques that they can bring to bear on their particular problem. So how might you go about disseminating work more widely? Well, you could look at publishing in a magazine or in a blog post. So magazines such as Mathematics Today, Higham News, LMS Newsletter, I'm sure there are plenty of other examples of places you could do this. The blog post could be a personal blog. Many research groups have their own blogs as well. And Higham News has a blog, so there's plenty of blogs around. And I usually find that Twitter is a good way to promote a blog post so that people can hear about it. So let me say a bit more about these two types of vehicle. So first of all, Mathematics Today. The IMA's magazine published 6 times a year. There's some wonderful articles in Mathematics Today. I've just picked out 3 here that I've particularly liked over the years. So the predecessor to Mathematics Today was the IMA Bulletin, of course. And I think the switchover happened in the 1990s. Some really wonderful articles in the old bulletins, in particular one by Jim Wilkinson, Error Analysis Revisited, which I think is a really nice article that I've often returned to. There's no new research in the article, but he has a very nice way of presenting how to think about and how to phrase error analysis. Another article I like is one by Julian Hunt on rounding. And he brings to bear his expertise from his time at the Met Office. And there's a number of points made about rounding there that I've never seen anywhere else. The last article here is about Google, really. Google was founded in 1998 around the idea of the PageRank algorithm. And over the years, there have been many papers explaining how PageRank works. One of the earlier ones, this is only 5 years after Google was formed, was by my brother Des and Alan Taylor. So this is explaining how PageRank works, and it's still, I think, one of the best available explanations. So the IMA Maths Today is certainly a wonderful place to publish. I do think these articles are probably not available actually online because it seems to be only the recent issues that are available online. So it would be nice if there was some way of making these and other older articles available, because I think there's some real valuable, some great nuggets in these older issues. So plenty of magazines. What about blogs? Well, let me just tell you a bit about my experience with blogging. So I've had a blog since 2013, and this is hosted on WordPress. Anybody can sign up for a free WordPress website and blog. If you go for the free one, the only disadvantage is that people who don't have a WordPress account will sometimes see adverts at the end of your blog posts. So you can pay for a personal or premium account that avoids that happening and has some other benefits. So I have different categories on the blog. And under the category of research, I've checked and I've published 22 posts over the time of the blog has existed. This was one from last autumn. So this was talking about large growth factors in Gaussian elimination, the paper I was just revising. And the great thing about blogs is that people can add comments at the bottom, just like the chat in this in these Zoom talks. So I got some comments at the end of the blog, one from Cleve Moeller, one from a user called Sandeep, and I was able to respond and respond to that feedback. So that's something you don't really get with a research paper, that instant feedback and the ability to interact with other people you may not even know. Now, our research group also has a blog on our Numerical Algebra website, and we encourage all the postdocs and PhD students to write a blog every time they write a paper. So here's an example from last year, a paper about analyzing the numerics of tensor cores and NVIDIA GPUs. And there's a blog post that gives a less technical description of what's in the corresponding paper. Now, early last year, I decided to start a new series of blog posts called What Is? And the idea was that I often just Google a term to find what it means if I come across a mathematical term I don't know. And quite often I just find a nice simple explanation. And I thought, well, maybe I could do a similar thing for areas I know about. I could write some very short blog posts that give a nice concise description of a particular term, a particular topic. And so in blue here is what I wrote down as my initial aim. And I wanted to do this with a minimum of symbols and equations and citations and just keep it really, really brief. So I've been doing this for a year. I've written 52 posts up to now. So I both provide a blog post, and also I make the article available in PDF form, downloadable from GitHub. You might know that the AMS has for many years had a What Is series of articles, not in every issue of the magazine, but sporadically. So these are 2 to 3 page articles. They're always on topics in pure mathematics, and they tend to be quite technical. So my aim was to be much less technical than those. So there's an example, a recent one. What is a diagonally dominant matrix? Let me just tell you about the workflow, because one thing you might immediately be thinking is, well, how do I get mathematics into a blog post? You know, because I'm used to writing in LaTeX. How can I do this with the blog? Well, WordPress has quite a good what you see is what you get editor, and it does support LaTeX. But you have to put the word LaTeX within $signs, and then your formula after the word LaTeX. So it's a little bit inconvenient. What I do though is I actually do everything in Emacs. So Emacs is a very old editor. You may have heard of it. It goes back to the 1970s, in fact. But it's still a very well-developed and very powerful editor, which can rival any other editor around today. And it has, as part of Emacs, something called org mode, which is a kind of markup language, very powerful, and it enables you to do things to write things that can then be exported into other forms. So what I do is I write my blog post in Emacs in org mode, and then if I want to print out a copy of the draft, I export it to PDF, which goes via LaTeX. There's one command and I get a PDF file. Another command will publish the post to WordPress using a package called org2blog that's available for Emacs. I could also, if I wanted to, export to HTML, just another key press, and that would be if I wanted to have a static page on my website. In that case, the HTML would use MathJax. I don't use MathJax for the blog posts simply because you need to pay for a more expensive version of WordPress in order to do that. But the built-in WordPress LaTeX support is quite reasonable. So that's what source looks like in my editor. So this is the source for a blog post. If you look at the bottom half of the screen, this just looks like regular LaTeX, and indeed it almost is. The only difference really is that the comment line is given by a sharp rather than a %, but this is otherwise just standard LaTeX. The bit at the top is just telling, is communicating with WordPress to say which post that Emacs is talking about, which date and so on. So going from that, with one key press, I can get a PDF version of that article, as shown here. With another key press, I can get the same thing in HTML form. And another key press, I can post that to my blog. And again, the WordPress is interpreting the LaTeX and displaying it in the form you would expect there. So that's how I do it, and that's I find a very nice workflow to use. Once you've gone to the trouble of setting up a blog, you of course want to know, well, is anybody actually reading it? What impact is this having? I think I've been helped a bit by a tweet last year from Neil Lawrence. Neil is the DeepMind professor of AI at Cambridge, and he posted this tweet to his 23,000 or so followers. And he's encouraging people who work on machine learning to read my blog, which is very nice. And certainly machine learning has a lot in common with numerical algebra. So a lot of the things I'm writing about, I think are indeed relevant to machine learning. So how do you know if who is reading your blogs? Well, on WordPress, you get quite a lot of statistics about the usage. And in particular, you can see what countries your readers are coming from. So here's a list of over the last year where my readers have come from. I'm not sure there's a lot to say about the list, but I noticed that, interestingly, India is third on the list here. There are very few people I know in India doing research in numerical algebra, and yet I've got quite a lot of readers from India. Of course, there are many people in India. China's much further down. And I think this may have something to do with certain sites being blocked, certain WordPress sites can be blocked in China. So maybe they had to use a VPN to access this. But you do get plenty of information about usage. But of course, the sheer numbers alone of views aren't everything. So how are people getting to my site was a question I asked. So I thought I'd do a little experiment for this talk. I would do a Google search on the title of some recent blog posts and see what happened. So this was done in Firefox in a private window. So a private window means Firefox doesn't know about your previous browsing history. So the results will not be influenced by any previous searches I've done. So what I did was, in both Google and in another search engine called DuckDuckGo that many people prefer to Google, I searched for these terms. And the first number is the ranking on the first page of my article, and in brackets is where Wikipedia appeared. So not surprisingly, Wikipedia was the first hit for both these searches. And in DuckDuckGo, my article didn't show up at all on the first page. For these search terms, I'm doing a little better, from second to fourth place. For these two search terms, I'm actually number one, interestingly. And especially interesting for this What is an LU factorization article, because that was only posted on the 20th of April. And I did this experiment on the 25th of April. So clearly, Google is rapidly re-indexing all the time, and things can quite quickly rise to a high position. And for these last two more specialist topics, there was no Wikipedia page at all appearing on the first screen of results. So, so that's quite pleasing. I was pleasantly surprised at the high rankings I seem to be getting from those articles, which means that if people search for these, if they ask these questions, they may well be directed to one of my articles. One other experiment I did was to do a search for a different term in Google. And the reason I did this was that this is a problem I've worked on a lot over the last 20 years, finding the nearest correlation matrix. And I have a paper in the IMA Journal of Numerical Analysis from 2002 that's one of my most highly cited papers. And I thought, I wonder what will happen if I search for this expression. And what I found was that my paper was second on the list, but a blog post I'd written was first. And this I thought was very odd. The blog post is very non-technical. There's no maths in it, it's just explaining the problem. It has a MATLAB code and a link to some other codes for solving the problem. But I was surprised that Google was ranking this above the paper, because to me, the paper is the more fundamental, there's much more in the paper than in the blog post. After a while, I think I realized why this is, and I think there's an important message here. So I went to my iPhone and I did the same search. And then I clicked on the link. So I clicked on the second link on my iPhone, and that's what I see. So I get the PDF file. And with my aging eyes, that's basically unreadable. Now I can pinch and zoom in and make it readable, but then I only see a few words at a time. So basically, apart from maybe checking an equation, I can't sensibly read an article like that on the iPhone. When I click on the blog link, I get that. And the reason is that my blog, being a WordPress blog, is what's called responsive. So depending on the size of the screen, the text is reformatted in order to make it legible. And then I remembered that Google is known to give prominence to mobile-friendly sites. So if you have a page that is mobile-friendly with this resizing capability, then it will give it a higher ranking. And so this is certainly a reason in favor of blog posts, that they are likely to be more easily found using Google and probably other search engines than something that's purely PDF. Now, one caveat about this, though, you might say, well, hold on a minute, the IMA journals hosted by OUP provide an HTML view of the article nowadays. And that's absolutely true, but that only came in at a certain point in time. So the older articles like this one from 2002 are PDF only. And so you will hit, with those, you will hit this problem of being penalized by in a Google search and not being so readable on a mobile device. So if your interest is piqued in blogging, then I'd strongly encourage you to just sign up for a free WordPress site. As I say, it's entirely free. You can get both a website and a blog, all part of the same site. I think if you want to start a blog, it's worth thinking about what your focus will be, what your niche will be. It's good to have something that's unique about your blog. Producing regular content is certainly something that will help get subscribers. A good way to make people aware of a blog post is to post them on Twitter. Just a single retweet from someone with thousands of followers will, rapidly get you a lot of potential readers. And because of the commenting facility, it's very easy to engage with an audience on a blog. And in the third edition of my Handbook of Writing, which was published last year, I actually have a chapter on writing a blog post. So there are more comments in there. So to finish off then, I hope I've argued that, at least for certain types of research, articles and blog posts can provide a very good way to disseminate that research more widely and to get it into the hands of people who might otherwise not see it. I also gave an example of disseminating unpublished work in this way. I wanted to mention an article by a psychologist called Hartley. So what he did, he wrote a blog post where he explained how he'd had a paper that was getting rejected from journals. And he decided instead to rather than keep trying to send it to another journal, he would recast it as a blog post. And he published it, I think it was the London School of Economics blog site. And he had 2,500 hits in the first few weeks from this rejigged, what was originally a research paper. Now, even if only, say, 5% of these hits were actual complete reads of the article, that's still over 100 people reading the article in the first few weeks. And I rather suspect that the average research paper doesn't get 100 readers in the first few weeks. It might get very few indeed. So again, this is an example of how a blog post can potentially have much wider reach than a research paper. So I guess my final word, I think we need more blogs and blog posts, as well as articles in the various magazines on applied mathematics. I'll leave it there. Thank you.
Okay, I'm working on the assumption that I can be heard. Oh, I can. I've got my face on screen, so I feel better about that. Thank you very much, Nick, for a fantastic lecture about a number of facets of your work and how we can try and improve dissemination. And we are on, as you know, you've spoken about the IMA publishing, and we work with OUP, and they have a separate social media department, and there's a bit of a gulf, I would say, between IMA editors and the OUP social media department, and articles that we write that get social media or greater prominence normally feature on topics such as the granularity of coffee or something like that. Mm-hmm. But you brought up some good points there. Now there's a couple of questions that we have. I can hear you, Nick. Can you read the questions, or is that just for me to read them?
Well, I can read it. So there's a question from David Abrahams. He's asking about where are we heading in the future? He said, I've made a good case for blogs. Will we actually need the gold standard of peer-reviewed published articles? Yes, I think we do. Blogs typically are, of course, not peer-reviewed. In the case of my blog, I can put anything I like on my blog. I typically do go through many revisions of my post, but it's just down to the person writing the blog to make sure that what they're saying makes sense. There's no peer review there. An organization may have a system for reviewing blogs, but it probably won't be as thorough as it would be for a journal paper. So I think blogs are really where they excel is for a more informal, less rigorous, maybe, let's say, approach. So I think the ideal really is to have the paper, as we always do, the gold standard, as you say, and use blogs to give another viewpoint, give a more general viewpoint, to maybe aim at a wider audience and to explain things in language that you wouldn't really want to use in a technical paper.
Thank you very much, Nick. So there's this separate Q&A chat that I can read. So there's a question here for you from Nick Trefethen. And it says, if you have a famous blog, as Professor Higham does, then it's a good means of communication. Can you comment, Nick, a bit more on what you're recommending for more ordinary researchers?
Well, a good way to start is by putting a blog on an existing blog. So there are many organizations like, for example, I know the AMS, the LMS, and Higham News has a blog. And Higham News, for example, encourages people to submit articles about research, and that will appear on the Higham website. So using somebody else's blog is a good way to start before maybe diving into having your own. If you do want to have your own, then there are plenty of famous examples to look at. Tim Gowers has a widely read blog, Terry Tao. But there aren't actually that many blogs at the research level. They're often much more at the education side or the undergraduate teaching side. So that's why really I'm saying we need more, particularly at the research level. But a good place to start would be by working with some existing organization who have a blog, and they might be happy to include something from you on theirs.
Okay, and I have another question from Robert Mackay. Robert says, what happens when the blog world gets as full as the publication world?
Well, of course, it is already, it's a big world, and it's even hard to know what's out there. Ultimately, the question is, how do people find things? And as I've indicated, blogs can be very findable via web search, just in the same way as papers via Google Scholar. I should say the Google Scholar does not index blogs. So if you want to find blog posts, you should really search on the regular Google search. But it does know about them. It will find them. So if you put good content out there, I think it will be found by people. But also promote it in any way you can via Twitter or whatever else, or via your website. Have links on your website to the blog post as well.
Okay, and another question. It's from an anonymous attendee, which I'm not so sure about, but nothing to worry about. How much interest do you get from the trading community to use your research to make money?
Well, this goes right back to the start in 2000 when I was approached by a London finance house who had this nearest correlation problem. And they said, here's the problem. You can either do it as a consultancy or you can do it not as a consultancy, and then you can publish whatever you do. So I chose the latter route, fortunately. And as I say, this became a well-cited paper. So everything I do is made publicly available. And of course, you never hear back from anybody who's using it what benefits it's had to them, unless you have a very specific link to somebody in a company. So it's very hard to know that recent post, for example, whether that trader is using this, or if so, whether it's really been useful for them. Unfortunately, it is very hard to get that sort of feedback from research that you make publicly available. But I would rather make it publicly available so that anybody can make use of it.
Okay, I think that's all the questions that we've received so far. So can I thank you, Nick, for an absolutely fantastic talk. And you moved into an area of mathematics, which is the promotion of mathematics that is something that we're all concerned about. I should also say that you publish a number of your papers through the IMA Journal of Numerical Analysis, where we meet annually, and each year we review the top cited journals, and your name pops up high on the lists, and we're very grateful for all of the material you've published through there. So with those few words, I'm not sure how we quite go on. Where's this? I need to shut something down. Raise hand. I don't know. We don't really have an applause mechanism, so perhaps I've missed that. No, we don't have anything on there for applause. So I'll just give you my own applause. And thank you very much, Nick. It's always been a pleasure working with you, and it was a great pleasure to listen to your expert talk today. Thank you, Nick.